Good morning, everyone, to this last section of the sixth Amazonian Symposium. Today, we are going to start with Pedro Cunha, and he is from the University of Aveiro, and is going to talk about hypershadows, imaging in 5 dimensions black holes. So here is.
Okay, thank you very much, Mercé, and good morning, everyone. Once again, it's a pleasure for me to be here, and I would like to thank also the organizers and Crispin in particular for the invitation to give a talk here. Today I'm going to talk about hypershadows. So essentially, this is the imaging of 5-dimensional black holes. I take it's a little bit kind of academic topic, but still it's something that I personally enjoy doing, even as a conceptual exercise. So we are going to follow essentially for the moment, this paper that is still on, it's on archive, is not yet published, but it was accepted for publication. So it will be published soon, together with João Novo and also Carlos Herdeiro. So as a disclaimer, although I'm going to talk about hypershadows, so imaging of 5-dimensional black holes, let me just say as a disclaimer, and also as a reference to Crispino's comment, apparently, not to my knowledge, there is kind of a character also called Hypershadow from the Sonic franchise. So let me just stress that any coincidence is just purely coincidental, okay? So I'm asking that no one sues me, please. So this kind of higher dimensional, seeing higher dimensional objects can be motivated, at least for me. I read this book, Flatlands, that I guess many of the people here might have heard of. So this is a book that is a romance of many dimensions. So the main character, and let me make a short summary of what the story is about. So the main character of this story is a square that lives on a plane in flatland. And as such, he has no concept of extra dimensions, namely the third dimension, in this case, the Z variable. And well, the story also serves as a critique of the Victorian society, if I recall. But at some point in the book, there is an interaction between the square and a sphere, a normal sphere in 3 dimensions. And it's very interesting the way it interacts. At first, the sphere talks to the square, but the square sees nothing. And at some point, in order to convey the idea of the third dimension to the square, the sphere, as depicted here in this drawing, which is actually from the book, the sphere kind of intersects with the flatlands, and then the square can perceive some kind of cross sections. And as the sphere moves up and down in the Z direction, well, the cross section which is a circle, increases and decreases in size in such a way to convey the idea of this extra dimension. So the exercise that I would like to do today is to try to understand a little bit better how we can perceive objects with one extra dimension beyond the 3 spatial dimensions that we are used to. Although it's not going to be exactly in this kind of cross-section process, which you can do, I would like to try to do something which is a little bit connected to the way that we perceive things with our own eyes. So let's start with that. How do we actually see things in our standard 3-dimensional world? Take, for example, this standard object, a 3-dimensional object. In this case, is a stop sign. So the light comes, so this is in flat space, okay? So light comes, it enters our eye, and it is projected on our retina, the back of our eye. So the point here is that this is a 2-dimensional surface, and you can kind of perceive this as a section of an S2 sphere. So I know the eye is not exactly spherical, that's beyond the point. What matters is that it can, locally, it's kind of a section of an S2 sphere. So in the end, the light is detected in the eye, and the electric signals are interpreted as an image. In this case, a two-dimensional image, which is connected with the dimensionality of this back part of the eye. Okay, so with this in mind, how could we, in principle, see something that has one extra spatial dimension? So a four-dimensional object. Can we then see such a four-dimensional object if we consider a three-dimensional retina? To be a little bit more precise, let me kind of recall what I mean by an S2 sphere. So in spherical coordinates, you can have the following parameterization, x, z, y. You have these spherical angles theta and phi with the standard range. So when I say the retina is a two-dimensional local patch, it is parameterized by the coordinates theta and phi. So it's not the whole sphere, it's just a local patch. So there is a generalization of the S2 sphere with one extra coordinate, is the S3 sphere. The formula is very similar. You just add one extra angle, so the pattern is very similar. You have cosine, then sine, sine, sine. It's very similar with the other angles. You start with the cosine, sine, sine, cosine, sine. So there is kind of a repeating pattern. So this, defines an S3 sphere, but you can, in a similar way to the S2 sphere, you can consider just a local patch, which is three-dimensional and can be parameterized by the three angular coordinates, so theta and phi, and also an extra angle, psi. So the idea would be the following. You have a standard three-dimensional space, and you are looking at a three-dimensional object, for example, a sphere. Then your eyes would perceive through your retina an image, a two-dimensional image, and the image itself would have a two-dimensional volume, okay? And the boundary of your image is a one-dimensional boundary, okay? This is, well, obvious in some way. Perhaps less obvious is then the four-dimensional case. But the idea is very similar. You have some kind of four-dimensional object, can be, for example, an hypersphere, and then the image that you perceive, your local retina, which is this volume, is the local patch of an S3 sphere. And in this case, the actual content of the image is a three-dimensional volume, and the boundary is a two-dimensional kind of surface. So this is something that you can actually perceive, is something that your brains can understand. So the point is, okay, you have a four-dimensional object that is difficult to imagine, but the actual image is something that you can conceptually understand through such a setup. So let me just define that an hyperimage is simply a three-dimensional image of a four-dimensional object. To get a little bit of a further understanding of these hyperimages, let me make another point, which is in our three-dimensional world, the angular size of an object typically decreases as the object is further away. It appears smaller to our eyes, and it typically scales as 1 over the distance. This is not exactly unexpected, of course. This is kind of depicted in this drawing here. And if you took a picture of an apple that is going further and further away, the angular size of the apple would decrease with the distance in such a way. So, taking this idea, in a four-dimensional world, the observed angular size of an object also decreases with the distance to the observer, although this is a little bit harder to understand or visualize. And surprisingly, it kind of decays in the same way with 1 over r. So for example, here, this is an example in flat space, let me stress that, of three-dimensional hyperimages of an hypersphere, so an S3 sphere. So to avoid confusion, let me stress there are kind of two different S3 spheres here. One is a local patch of kind of a retina, and the other is the actual object that is being perceived. Okay. So if you look at this hypersphere at some distance, you see, well, a sphere. That's the image of an hypersphere. It's not really surprising, I guess. But the image is not just the boundary, it's actually the whole volume. And as the distance to this S3 sphere increases, the size of the image diminishes. Just in the same way that you'd expect for an image in three-dimensional space. It decreases with size. But here is the volume of the image that decreases. But the main idea is the same. So, can we take this concept and now have a true sense of what an image of a higher dimensional black hole is? So, first let me motivate why we should consider even extra dimensions. I'm going to be fairly brief on this point, but the thing is that taking extra dimensions beyond the standard four-dimensional in gravity can introduce unexpected modifications and often has a very rich landscape of both solutions and phenomenology. For example, there are some indications that there is a violation of cosmic censorship, namely weak cosmic censorship, when you go to dimensions, to gravity with dimensions higher than 4. Namely, you have some black hole horizons in vacuum that can develop instabilities that can lead to naked singularities. So there is kind of indication that the weak cosmic censorship can be violated in dimensions higher than 4. Where for 4, this is not exactly clear, at least from a general initial conditions, data conditions. Another thing is the possibility of having more diverse type of topological horizons. So it's with dimensions higher than 4, event horizons can have different topologies. So in addition to having spherical topology, they can also have, for example, toroidal topology, have black rings. And interestingly, in contrast with the 4 dimensions, so we have for which you have uniqueness. So if you, in 4 dimensions, if you have vacuum, general relativity, and stationarity, this implies essentially that you have Kerr metric if you have no charge. So there's kind of a series of uniqueness theorems that forces you to have that. But there is no such equivalence of uniqueness theorems in higher dimensions, which is interesting. So, and this can be realized because you can have black rings, as I mentioned. They have a toroidal horizon. They are not spherical in the topological sense. And these solutions in vacuum can coexist with spherical solutions for the same mass and spin. So there is no uniqueness anymore. So in particular, for these topological spherical horizons, they are kind of the generalization of the Schwarzschild Kerr metrics. They are the Tangerlini and the Myers-Perry black holes, which both have spherical horizons. And in particular for the Myers-Perry, it's what I'm going to focus next. So the Myers-Perry solution has actually generalizations for a lot of dimensions. I'm going to focus on the particular 5-dimensional case and with equal spins. Because the thing is, when you go to higher dimensions, in contrast with Kerr, where you have only one spin parameter, here you could in principle have 2 different spins. You can have two independent orthogonal planes with angular momentum. So the black hole can rotate in 2 different ways at the same time. So the metric is a little bit more evolved when you have 2 different spins. It simplifies a lot when both spins are equal, which is the case here. So this is the metric of this kind of Kerr generalization with 1 extra dimension with equal spins. there is this kind of theta, phi, and psi coordinates. These are actually not spherical coordinates, and you can realize that when you go to the far field. But before mentioning this, let me just stress that these black holes are topologically spherical, and they have well-defined mass, which is given in terms of this parameter mu. So this parameter mu that appears, for example, here is the mass parameter. It's not exactly the mass, but is correlated with the mass. And this small parameter a essentially is the spin parameter. Okay, that's what I wanted to say. So these are 5-dimensional black holes, but they are 4 spatial dimensions and then 1 time dimension. So essentially, we are going to obtain the images of these black holes. We are going to suppress the time dimension because these solutions are stationary. The non-trivial part is to obtain the 4-dimensional images. So, as I mentioned, these coordinates are not spherical because if you look at the metric in the far field, so with this x coordinate being very large, you first realize that this x is the radial coordinate squared, and that this angular component is not the metric that you would expect of an S3 sphere in spherical coordinates. It actually describes an S3 sphere, but in Hopf coordinates. So these are not spherical coordinates. Something which is intriguing is that if you take this theta angle to be constant, the surface that you get is a 2-dimensional surface covered by the angles theta and psi that describe a 2-dimensional torus. So it's a little bit hard to imagine, okay? But, well, to obtain this solution, this specific type of Hopf coordinates have some special properties that lead, for example, to integrability of the geodesic motion. So, some comments about the symmetry. So this 5-dimensional Myers-Berry solution, it has 3 Killing vector fields. You can compare that with Kerr. It has 2 Killing vector fields, one in the time direction and another in the azimuthal direction. In this case, in addition to those two, you have 1/3 Killing vector field connected with the psi direction. So in a similar way to Kerr, this leads to Killing constants of motion along the geodesic motion, kind of the energy of the particle, and then 2 different angular momentum connected with the 2 rotation axes that you have. And in a similar way to Kerr, you have also a non-trivial constant of motion, so a Carter-like constant. So this makes the geodesic motion completely integrable. This last part is not necessarily guaranteed if you consider other black hole solutions in 5-dimensional gravity, for example, the black string. As far as I'm aware, there is no such Carter-like constant. I could be proven wrong, of course, but to my knowledge, that is not the case. So, since the motion is fully integrable, you can actually write the null geodesic equations, so again, with equal spins in this way. So, this dot is a derivative with respect to an affine parameter along the null geodesics. It's something fairly compact, and that can be worked out to obtain interesting results. Namely spherical photon orbits. So why is these spherical photon orbits? Let me give you some context. In the Kerr case, in 4 dimensions, the shadow of the Kerr black hole is determined, so the image of the Kerr black hole is determined by a set of photon orbits that have a constant radial coordinate. The same thing will happen here in the Myers-Berry case. They will define this hypershadow. And in a way very similar to Kerr, the spherical photon orbits will be determined by these 2 conditions. First, that the motion along the theta coordinate is real. Okay, this is not immediately guaranteed. This actually places a restriction on your motion, because the theta motion and the radial motion are kind of decoupled because of integrability. So this condition actually places a physical constraint for the constants of motion that you have. And then you have two equations that restrict the radial motion. So essentially, in simple terms, you have no motion locally in the radial coordinate, and also kind of the acceleration is also zero. So with these three conditions, you get a set of equations that you can actually solve analytically and give a very nice result. I don't want to bother you with too much technical details, but I encourage you to check the paper if you are interested. But I will jump into the conclusion. If you look at the physical domain of these spherical photon orbits in the Myers-Sperry spacetime, you obtain something like this. So this is the complete family of these spherical photon orbits. It's a two-dimensional family. They depend on the angular momentum, actually on the difference between the angular momentum of the photon on both directions, on both rotation axes, depend on the radial coordinate. So at each radial coordinate, you have an entire family of spherical photon orbits with different angular momentum. What's represented here in the z-axis is the amplitude, so the variation that each spherical photon orbit has in the theta coordinate. And you can notice that the frontier of this physical region is a set of spherical photon orbits that have zero amplitude in the theta coordinate. These are the generalization of the light rings. So they are essentially motion of null geodesics that have motion both in the theta and phi coordinate and also in the time coordinate, but don't have any motion both on the radial and latitude theta coordinates. And it's interesting because you can compare this with the Kerr case. In the Kerr case, as kind of a reminder, this would be the equivalent photon region. So you have two light rings at the border, and in between you have these spherical photon orbits with some theta amplitude, and this theta amplitude is zero at extremities. So this is kind of one-dimensional family. But now in the Myers-Sperry case, we have a two-dimensional family. But in a kind of very curious way, the boundary of this family is still given by these kind of light ring generalizations. Although, as you will soon see, these light rings are not born equal. They don't have the same kind of importance for the shadow. To actually compute the image of a black hole, you need to consider and define some observation frame. So in the Kerr spacetime, there is a very natural observer, which is a Zamo observer, which is a zero angular momentum observer. In the Myers-Sperry spacetime, you can find a generalization of this, although it's a little bit more subtle, but you can define this. And then, so you have some tetrad here, these E's, which define your observation frame. And then you can project the momentum of the photon onto this tetrad to obtain locally observed momentum quantities. So this is the P with the kind of parenthesis on top. This is what an actual observer would see the momentum of the photon. Then you can take this and connect with local image coordinates. These will be these capital X, Y, and Z. So remember, this is a three-dimensional retina, so you need three observation angles locally. That is it. And then you can connect with these kind of momentum quantities along the different directions. There is a multiplication here of a square root of the x coordinate of the observer for a very simple reason. So x, I mentioned a few slides before, is essentially the radial coordinate squared. So I'm essentially multiplying here by the radial coordinate. That makes sense because the angular size of images decays with 1 over r. So if I multiply the angle by the radius, I get something that has a well-defined value for very large distances. which is what I'm going to do. I'm going to put the observer very far away from the black hole. So I want to define some kind of observation coordinates that have a well-defined limit in that context. So if you do these calculations, you can obtain essentially the parameterization of the hypershadow in these very far away limits. So when this x coordinate goes to infinity, you obtain a fairly simple expression for the image coordinates x, y, and z, where this Carter constant and the two angular momentum of the photon, they are constants of geodesic motion, but they are determined in a parametric way by the spherical photon orbits. So, with this introduction, now let me introduce you, for the first time, the 5-dimensional hypershadow of the Myers-Berry spacetime. So this will be a 3-dimensional image. So you can look that in some way it looks remarkably Kerr-like. This is for an extremal Myers-Berry black hole. You can see, like Kerr, one of the faces is slightly squashed, but this is something that you can perceive and understand with your eyes. And this is the true image of a Myers-Berry black hole that a being with a 3-dimensional retina would see. So we can dissect this image a little bit more. So this is a plot of the 2-dimensional surface boundary of this Myers-Berry hypershadow. The hypershadow is this larger surface here. Inside, we have placed a reference sphere so you can understand how this is deformed. And in addition, you can see how the spin affects the shape of these images. So in red, in blue, you have almost Tangerlini-like black hole, so that would give you a simple sphere. Not that interesting, I would say. And then as you increase the spin to close to extremality, you reach an hypershadow which is very kind of squashed on the side. Very much like in the Kerr way. You can notice that there are 2 points here highlighted, one in red, another one in green. I'm going to call them light points for a reason that will become clear in a minute. So this green point is light point 1, this is light point 2. And what's interesting is that they have a connection with the spherical photon orbits, a very simple connection. This green point here is determined by one orbit here, one of the light ring orbits here. Not specifically one, it can be one of them, because you can have the observer at different theta, with different observation angle theta. That will change the light ring that is being used to determine this point. But remarkably, the shape of the hypershadow does not depend on the observation angle, which is kind of surprising. In the Kerr case, the shadow that you observe, the image of the black hole, depends on the observation angle. In this case, it does not. The shape is always the same. The other point is, in a similar way, is determined by the outermost light rings, shown here in the red. Something that perhaps is not very obvious, and especially not in the image that I showed before in the video, is that this hypershadow has always a symmetry along the axis between the light points. So that's why we define the light points, because it's useful for this discussion. So between these 2 light points, there is an axis, and then the shadow has a symmetry axis along that axis. And you can actually explore this symmetry. This is not a very obvious symmetry. Actually, João at some point mentioned, oh, this looks, that has a symmetry and so on. So we made some calculations, and indeed you can prove that it has an exact symmetry, although it's not very obvious why. But you can explore this to have a very simple parameterization of this hypershadow of the Myers-Berry spacetime. It's just this, depends on two parameterization coordinates, the radial coordinate and some auxiliary angle. And then these q and alpha, they are functions of x and the spin. And that's it. And you can play with Mathematica and you can obtain an exact representation of this hypershadow for any observation angle and for any spin. And it's quite remarkable. It's in some ways much simpler than in the Kerr case. So what lies ahead? So I'm not claiming any connection with astrophysics because this is mainly a conceptual exercise, which I think open doors to further understand some properties of higher dimensional objects. But you can question, ask some questions right from the top of my head. For example, black rings, like I mentioned, they have a toroidal topology. What is the hyperimage, the true image of these solutions? Are they a three-dimensional torus? I don't know. In that case, probably you don't have integrability, so you have to resort to numerical methods. But it's an interesting question for me. Another one, like I mentioned, there is this continuous symmetry, this axis of symmetry in the hypershadow. To me, it's not very clear why, what's the reason for this? Is there a deeper symmetry property here? Is this connected only with the fact that we have considered two spins to be equal? I don't know. It's future work, I guess, for someone that is interested. Okay, I still have plenty of time, I guess. So could the chair confirm? Yes, okay, thank you. So this was my main part of the talk. But I'm going to give a bonus talk now, if I may be allowed to do so. Also because of the public lecture that I gave yesterday, afterwards some people asked me for further details, and I thought this could be a good opportunity also to explain a little bit better in English for those that did not understand what I was saying in Portuguese, and also just to give some further details. So what I'm going to discuss is the image of the gravitational collapse of a pressureless star into a black hole. So essentially, this is, in practice, the metric that I'm considering here is the collapsing of dust matter. So this is kind of an Oppenheimer-Snyder kind of collapse. Not exactly, because in the original paper, it started from rest at infinity. And here I want the dust to start from rest at a finite radius. So the metric looks like this. You have the proper time tau. You have this capital R, which is the cool-moving dust radius, so in the dust frame. And then you have this small r, which is the areal radius. So in this case, a dust particle world line has this capital R constant and also theta and phi, which is kind of condensed here in the two-sphere kind of part. To obtain a solution here simply means obtaining the small r as a function of the co-moving radius and tau. And the same thing for this lambda here. And it turns out that it is possible, so this is a problem that has been studied lots of times. It's possible to find analytical solutions with the dust starting from rest at some finite radius, and when tau is equal to 0. And essentially, this is what we have. And outside the star, we have Schwarzschild, essentially. And to image the star, you need to convey it with some luminosity profile. And what was done is to consider simply black body radiation with some constant temperature T. So essentially for a given wavelength lambda, you have essentially these spectral radiance. But then you can ask the question, okay, I have this. How can I know the color, the perceived color of the star with my own eyes, given some spectra, namely this spectra? From the top of your head, this might not be completely obvious well, it's an obvious question, but doesn't have a completely obvious answer, I would say. So this requires just a brief introduction to colorimetry, which I am by no means an expert, but well, I looked a little bit into the details, and I will try to explain the best I can. So how do we actually perceive color? So in our eyes, in the retina, you have 4 types of cells that detect light, and that gives you information for vision. You have 3 cone cells for color vision, and then 1, the rod cells that are useful when the intensity of light is very small. But for color vision, what matters is these 3 cone cells, which in a way embody the perception of red, green, and blue. Okay? So the point is that your eye has 3 types of color sensors that will respond to different ranges of wavelengths. Not exactly one, it's not a delta, it's a distribution. So this problem was analyzed and considered by the so-called International Commission on Illumination, and that published in 1931 a paper and a report that defines some color spaces in such a way to define a well-defined relationship between the visible spectrum and the visual sensation of specific colors by the human color vision. So how does it work in practice? You have these kind of sensitivity curves that in some way are connected with the blue, red, and green. You can think of these 3 cells as detectors, as artificial detectors, and have different sensitivity curves. And then you have to project your spectra over these different sensitivity curves to give your perceived color perception. In practice, what you do is something like this. You have the perceived stimulus of light by the cones for what is defined as a standard observer is given by this. You have 3 stimulus values. These are not image values, by the way. This is just the nomenclature that this commission used, these capital X, Y, and Z. So you make an integration over all wavelengths of your spectra. That doesn't have to be necessarily black body radiation, can be anything, and then weight it with these kind of functions, the sensitivity functions. This defines you kind of 3 weights, capital X, Y, and Z, which approximately kind of convey the red, green, and blue perceived colors. Although this is not exactly true, it's a little bit more complicated. There is a mapping then that you can do between these X, Y, and Z to red, green, and blue, but you can take my word for it that it gives more or less a good approximation. So if you now take a black body spectrum and you use this kind of methodology to make a prediction of the perceived color, you'd get something like this. Something which is, well, familiar to you, I guess. For a black body with a very small temperature, you virtually see nothing because although it emits light, its intensity will be very small, and in the end we'll perceive black. Then you get some reddish kind of thing, then oranges, orange-like color, and then for very high temperatures you get kind of bluish color. So, and that's it. And then making just a connection and explaining a little bit better for the people that yesterday could not speak Portuguese, the expectation for the collapse of a star would, in principle, look something like this. You have the angular size of the star decreases. You would expect some reddening because of redshift until you get kind of the shadow of the black hole. But this is not exactly like this because different parts of the star will get light at different times because the redshift will be connected with the radius of the star at some given point. And so in practice, what you would actually see is a higher redshift starting from the center outwards. And then, well, let me show the video again. So for now with that perception. This is for a neutron star-like star collapsing, and then you can see the reddening, the redshift, and then you have the black hole. And yeah, that's it. Thank you very much for your attention.
Thank you very much, Pedro. Are there any questions? No? I have one about the first part of the talk.
Okay.
And it's because you are focusing on the 3D image, let's say, or shadow. But at the end of the day, we observe two-dimensional things. Because we're going to take a picture, so it is projected.
Yeah.
So is there any way that we can see something different depending on the projection of this 4D, well, 3D to 2D?
Yeah. So from the practical point of view, as far as we know, we live in a three-dimensional world with one-time dimension. So I would say that the main motivation, at least, to do this work was conceptual. That being said, I think it's scientifically kind of good to be open-minded that perhaps we live in a higher dimensional world. We simply do not perceive it. If that is the case, for example, if you have some kind of higher dimensions that they are not easily perceived, this sort of exercise could be proven useful, I guess. How you build such a detector to kind of perceive these sort of images, that is beyond my understanding. But yeah, that's all I have to say.
Yeah, but the thing is that you could always project or lower the dimension to...
You can, and in principle, you can have kind of a tomography of these higher dimensional objects, and you get two-dimensional images. But the true image that has kind of the most symmetries is this full three-dimensional object. That, in a way, it was surprising. It is full of symmetries in this case. Does not depend on the observation angle, has a rotation axis, and a lot of other properties. And this would be very difficult to perceive and understand if you were taking this kind of tomography approach. So I think this could prove useful not only to understanding the images of black holes, but also other objects that have higher dimensions. There could be some way of better understanding, because the human mind is very intuitive in some ways. Although you can make calculations that not depend on visualization, having an intuition of seeing things, I think it can prove useful. So if you, for example, you have some kind of plot that is four-dimensional, you say, okay, it's difficult to see and so on. In principle, you can use one of these techniques to get kind of a more close understanding of what's going on. Yeah, that is my take.
Thank you very much.
Thank you.
Any other...
Hi, Pedro. Thank you for the talk. My question is about that axis of symmetry that emerges in your first part. So this additional coordinate that you introduce is a cyclic one, right?
Yeah.
So is there any relation between this coordinate being cyclic, so with and this axis of symmetry?
So this
or this is something else?
Yeah. So the thing is, no, I don't. Well, this V. I don't recall the Greek name for this letter. No, it doesn't matter. Upsilon, perhaps? I don't remember. Mu? New. No, it's not exactly new. Okay, let's say it's new. So this new angle is a cyclic angle along this axis of symmetry. It's an auxiliary angle used to explore the fact that we know that there is this symmetry. Okay, has no special meaning in principle. You could connect it with other quantities, namely the angular momentum and so on, but there is not a trivial connection. So it's.
This mu is not the extra dimensional coordinate.
No.
No, these are some just a parameter to that you introduce.
Yeah, because you don't, in principle, you don't need this. If you can use a standard parameterization of the hypershadow, which is very much curl-like, something like this. So this is very much curl-like, as you probably can recognize. So you have theta and psi, and then the Carter constant that depends in a parametric way by the spherical photon orbits, which, if you remember the discussion, is a two-dimensional space. So this will give you also a two-dimensional surface. Okay, and it works. Actually, the video that I showed is done using such a parameterization, but it's a little bit contrived. If I try to put in one slide all the expressions, it's a little bit contrived and a little bit opaque. But since you have this continuous symmetry, you can explore it by defining this angle. You just have to define the contour in a slice that crosses the axis. And then, because of this symmetry, it's just a simple rotation. So it's kind of an auxiliary angle. Has, as far as I know, no deep meaning. Okay, I tried to see if there was a connection with other quantities, and it's not very obvious.
My question is because first you take care, 1 plus 3 here, you have one cyclic coordinate. And in the image, if you plot like a 3D, not a 2D image, but a 3D shadow image, this also has this X of symmetry in the shadow, right? Which is due to the cyclic coordinate. So if you rotate along the phi direction, this essentially gives you an X of symmetry in the shadow. So I was wondering if this new X of symmetry is related to this new cyclic coordinate that you introduced in your extra dimension.
It's difficult to say. So the fact that in curve, for example, you have this phi coordinate, which is cyclic, doesn't imply necessarily that the shadow is symmetric with respect to phi. What it means is that when you move your observer in the phi direction, the shape does not change. And here, indeed, if you change the observer in both theta, phi, and psi, the shadow never changes also. Or it can at most rotate in this three-dimensional image space. But the shape is always the same, which is also surprising. But again, regarding the origin of this symmetry is not very clear. If I had to guess, it could be connected with this, the fact that we assume that both spins are equal. But yeah, other than that, I don't know. But it can be explored in this case. We have a very nice parameterization.
So a second question about the second part.
Okay.
So when you have this collapse and the surface of the star crosses 3M,
yeah.
So you have the emergence of a light, right?
Yeah.
So and then you have the star still to collapse, but now with a radius less than 3M, it emits a light. So these lights get trapped into the light.
Yes.
So essentially you have so in the light ring a movie there about this final stage of the collapse. So can we see this in the movie?
Yeah. So
like this last like the
moments.
play of the last stage of the collapse.
So let me dissect the movie part by part. So you have the star, okay?
Yeah.
So it starts to collapse, and then if you look closely, it's difficult to angular size the envelope kind of freezes. It's still emitting, okay. But at some point it has crossed the 3M part. But in the other movie, actually, this was perhaps a little bit more apparent. So it kind of freezes. It's still emitting, but then you start to having larger and larger redshifts going from the center of the image outside. And the last part for you to detect brightness is actually the outermost thin layer, which is precisely connected with these light ray orbits. So you can see that. Yeah, the radius. Yeah, so it's kind of frozen the size, precisely because the star has crossed the 3M. Everything has to be consistent.
Thank you.
Thank you.
Okay, do we have time for one more question? If not,
Thank you very much.